The first atomic model soon after the discovery of the electron is the plum pudding model, which was proposed by J. J. Thomson in 1904.
The model tried to explain two properties of atoms then known, that electrons are negatively charged particles and that atoms have no net electric charge. The plum pudding model has electrons surrounded by a volume of positive charge, like negatively charged plums embedded in a positively charged pudding. In this model, the electrons bound by electrostatic force orbit freely and stably under classical mechanics.
Other atomic models are proposed as well. Joseph Larmor created the first solar system model of the atom in 1897. Jean-Baptiste Perrin suggested a same model in his paper dated 1901.
In 1904, Hontaro Nagaoka proposed an alternative planetary model of the atom in which a positively charged center is surrounded by several revolving electrons, in the manner of Saturn and its rings.
Both models made two predictions. First, a very massive atomic center, in analogy to a very massive star of planet. Second, electrons revolving around the center, bound by electrostatic forces, in analogy to the rings revolving around Sun or Saturn, bound by gravitational forces. However, both models lacked experimental evidence of the massive atomic center, known as atomic nucleus today.
The discovery of atomic nucleus was related to the study of radiation. In 1896, Henri Becquerel found that rays emanating from certain minerals penetrated black paper and caused fogging of an unexposed photographic plate.
This behavior is very similar to the X-ray from discharge tube discovered by Wilhelm Röntgen 1 year before.
However, Becquerel's doctoral student Marie Curie discovered that only certain chemical elements, such as uranium, gave off these rays of energy.
Such behavior is definitely different from the X-ray. Marie Curie named it radioactivity. In 1899, Ernest Rutherford used a generic uranite radioactive source, a uranium-rich mineral formerly called pitchblende, to determine that the radiations had differing penetrations in materials.
One type had short penetration, stopped by paper, and a positive charge, which was named alpha rays. Rutherford and Thomas Royds proved in 1909 that particles in alpha rays, alpha particles, are ionized helium. The other was more penetrating, through paper but not metal, and had a negative charge.
Rutherford named it beta ray.
Beta ray was the radiation that had been first detected by Becquerel from uranium salts. Becquerel himself proved that beta rays are fast electrons. In 1900, Paul Villard discovered a third especially penetrating and charge-neutral type of radiation from radium. Rutherford realized that it must be yet a third type of radiation, which were named gamma rays in 1903. Rutherford and Edward Andrade proved in 1914 that gamma rays are electromagnetic rays like X-rays, but with shorter wavelengths.
Between 1908 and 1913, Rutherford and his colleagues, Hans Geiger and Ernest Marsden, performed a series of experiments in which they bombarded thin foils of metal, such as gold, with alpha particles. They spotted alpha particles being deflected by angles greater than 90 degrees. To explain this, Rutherford proposed that the positive charge of the atom is not distributed throughout the atom's volume as Thomson believed, but is concentrated in a tiny atomic nucleus at the center. Only such an intense concentration of charge could produce an electric field strong enough to deflect the alpha particles as observed. Note that Rutherford model didn't attribute any structure to the remaining electrons.
As early as 1815, William Prout proposed that all atoms are composed of hydrogen atoms, based on the observation that the atomic weights that had been measured for the elements known at that time appeared to be whole multiples of the atomic weight of hydrogen. In 1886, Eugen Goldstein studied gas discharge tubes which had perforated cathodes. When a voltage of several thousand volts was applied between the cathode and anode, faint luminous rays were seen extending from the holes in the back of the cathode. These rays are beams of positively charged ions produced from gases, which moved in a direction opposite to the cathode rays. They are called anode rays. The glow was caused by their collision with other charge-neutral particles. Wilhelm Wien in 1898 identified the hydrogen ion in the anode ray as the particle with the highest charge-to-mass ratio in ionized gases. Following the discovery of the atomic nucleus, Antonius van den Broek proposed that the place of each element in the periodic table, that is, its atomic number, is equal to its nuclear charge number, that is, the nuclear charge in whole number units of elementary charge.
This was confirmed experimentally by Henry Moseley in 1913.
In 1917, Rutherford proved that the hydrogen nucleus is present in other nuclei, a result usually described as the discovery of protons.
Rutherford realized in 1925 that the alpha particles are absorbed when they are introduced into pure nitrogen gas.
After a nitrogen nucleus captures an alpha particle, a hydrogen nucleus is ejected, resulting in an oxygen nucleus. This was the first reported nuclear reaction. He named this new fundamental building block of the nucleus the proton, after the Greek word for first. Rutherford suggested that the nucleus consisted of positive protons and neutrally charged particles, based on the observation that the charge-to-mass ratios of every other nucleus is lower than that of proton.
In 1921, William Draper Harkins first named the hypothetical particle neutron.
In 1931, Walther Botha and Herbert Becker found that, if alpha particle radiation from polonium fell on beryllium, boron, or lithium, an unusually penetrating radiation was produced, which was not influenced by an electric field. In the following year, Irene Joliot-Curie and Frédéric Joliot-Curie showed that, if this radiation fell on paraffin, or any other hydrogen-containing compound, it ejected protons of very high energy. Sir James Chadwick quickly performed a series of experiments that showed that the new radiation consisted of uncharged particles with about the same mass as the proton. These particles were neutrons. In summary, an atom is composed of a positively charged atomic nucleus, with negatively charged electrons surrounding it, bound together by electrostatic interaction. Almost all the mass of an atom is in the atomic nucleus, with a very small contribution from the electrons. The atomic nucleus is the small, dense region consisting of protons and neutrons at the center of an atom.
Its dimension is much smaller than the diameter of the atom itself, by a factor of tens of thousands.
The atomic number of an atom, symbol Z, is equal to the proton number in the atomic nucleus. For example, an atom with 6 protons in its atomic nucleus has an atomic number of 6.
A chemical element is a species of atoms that have the same atomic number. It takes a position in the periodic table. For example, element carbon consists of atoms with 6 protons in their nuclei, that is, atoms of atomic number 6. In an uncharged atom, the atomic number is also equal to the number of electrons.
For example, a carbon atom has 6 electrons. Proton and neutron are both called nucleons.
The nucleon number of a nucleus defines its mass number, symbol A.
It is the sum of proton number and neutron number, symbol N. A nuclide is a species of nuclei that have the same proton number and nucleon number.
A nuclide is named with its element name followed by its mass number.
For example, the nuclei with 6 protons and 6 neutrons in their nuclei form a nuclide, called carbon-12, as its mass number is 12. The nuclei with 6 protons and 7 neutrons in their nuclei form another nuclide, called carbon-13, as its mass number is 13.
The isotopes of an element are atoms differing in mass numbers due to different neutron numbers in their nuclei.
Thus, each isotope corresponds to a nuclide. The isotopes are named using the corresponding nuclides. For example, carbon-12 and carbon-13 are isotopes of element carbon. Note that the nuclide concept emphasizes nuclear over chemical properties, while the isotope concept emphasizes chemical over nuclear properties. The neutron number has large effects on nuclides' nuclear properties, but its effect on isotopes' chemical properties is very small. For example, the nuclear properties of carbon-12 and carbon-13 are distinct, but their chemical properties are very similar. One way to convey the atomic number and the mass number of a nucleus, atom, nuclide, or isotope is by using nuclear notation. A nuclear notation shows the chemical symbol, symbol X, the atomic number in the left subscript position, and the mass number in the left superscript position. The atomic number is redundant to the chemical element, so it can be omitted, but is sometimes used to emphasize the change of proton numbers in a nuclear reaction. For example, carbon's atomic number, 6, can be omitted. Carbon has 3 common isotopes with mass numbers 12, 13, and 14, respectively.
Their nuclear notations are shown below.
Now, let's look back at the nuclear reactions. In alpha decay, a nucleus emits an alpha particle and thereby decays into a different nucleus. An alpha particle is identical to a helium-4 nucleus, which consists of 2 protons and 2 neutrons. In a nuclear reaction, charge is conserved. However, mass is not conserved. According to general relativity, in nuclear reactions, mass and energy convert from one to the other. Nevertheless, the change of mass is tiny compared to the total mass, so both the atomic number and the mass number are conserved. Thus, in alpha decay, the mass number is reduced by 4 and the atomic number is reduced by 2. For example, the decay from uranium-238 to thorium-234 is an alpha decay. In beta decay, a beta particle, fast energetic electron, is emitted from a nucleus.
The mass number is unchanged, and the atomic number is increased by 1.
For example, the decay from thorium-234 to protactinium-234M is a beta decay. Here, M stands for a nuclear isomer, which is a metastable state of a nucleus. Electron has -1 elementary charge and negligible mass compared to any nucleus, so it can be written with a nuclear notation with atomic number -1 and mass number 0.
A neutrino is also emitted in beta decay.
But its mass and charge are both 0. Thus, it is not discussed in chemistry. A nuclear isomer can then decay to a lower energy state by emitting a gamma-ray photon in a process called gamma decay. For example, the decay from protactinium-234M to protactinium-234 is a gamma decay. The above-mentioned examples are the first steps of the uranium series.
That's why the decays can be observed from uranite.
In the discovery of proton, a nitrogen-14 nucleus captures an alpha particle and ejects a proton, so that an oxygen-17 nucleus is the result.
In the discovery of neutron, a beryllium-9 nucleus absorbs the alpha particle and ejects a neutron, so that a carbon-12 nucleus is the result. Neutron is a nucleon with 0 charge, so it can be written with a nuclear notation with atomic number 0 and mass number 1.